Hello, my name is Deborah, and I will present our paper, SeaThru-NeRF, Neural Radiance Fields in Scattering Media. Modeling scattering media in an image synthesis framework such as neural radiance fields leads to superior scene restoration. Here is one of our results where we render the same scene, both with and without the medium. We achieve our image restoration by removing the medium. Neural radiance fields provide a powerful approach to leverage neural network for the synthesis of novel views. NeRF's framework includes tracing rays from input images, sampling points along those rays, using an MLP network to predict color and density for each sample, and performing alpha compositing to render a pixel. By virtue of its ability to predict the color and density of samples along rays, the network possesses an intrinsic capability to model the properties of a scene's medium. This is particularly relevant when dealing with scattering media, such as water. With the ability to model the medium, it becomes feasible to remove it from the scene. Does it work with the state-of-the-art NeRFs? We trained MIP-NeRF 360 by Baron et al. With images of an underwater scene, and this is the result. The water was modeled as an additional blue object. In our work, we developed a medium-aware NeRF, which is capable of correctly rendering novel views in scattering media. In order to understand why state-of-the-art NeRFs are limited in scattering medium, we need to understand what happens to light traveling from an object to the camera through such media. For the purpose of this presentation, we will specifically concentrate on water as a representative medium. Underwater, the light captured by the camera consists of two distinct additive components. The first component, known as the direct component, originates from the imaged object. However, as it travels through the water column, it experiences attenuation caused by absorptions and scattering, resulting in a decrease in intensity. The second component is the backscatter, which is an additive signal that degrades the image quality. This component arises from light reflecting of particles suspended in the water column. In our work, we employed a revised model proposed by Kainak and Travitz in CVPR 18. In this model, the coefficients for attenuation and backscatter are not identical. In the original rendering equation of NeRF, the computation of pixel color involves summing up contribution from each segment of the ray. Each contribution comprises the color of the segment Ci and is weighted by the estimated transmission Ti. The transmission represents the amount of light blocked along the ray's path, while the emitted light from the segment is determined by the alpha value alpha I. However, these equations do not take into account the characteristics of the medium, particularly the additive signal contributed by the medium itself, aka the backscatter. As a result, it is not surprising that NeRF in its current formulation exhibits limitation when it comes to handling scattering media. In our research, we have made significant progress by developing a medium-aware NeRF model that not only models the object in the scene, but also considers the properties of the medium between these objects and the camera. In our model, we maintain continuity of the medium's properties along the entire ray, extending until the end, as visually depicted in the figure. Our research introduces two primary innovations: novel rendering equations that accounts for the medium properties, and an additional module for modeling medium properties within the network architecture. In our medium-aware rendering equations, the color of a pixel is determined by the combined contribution of the object and the medium. The object's color component is akin to the original NeRF formulation, but with an additional factor accounting for the color attenuation caused by the medium. On the other hand, the color of the medium is computed as the sum of contribution from each segment along the ray until it encounters an object. If no object is present, the pixel's color will solely be determined by the color of the medium. In our formulation, the properties of the medium, including color and densities, remain uniform per ray. Our network architecture is built upon MIP-NeRF 360 by Baron et al. We extend this architecture by incorporating a dedicated medium module. The additional module predicts the properties of the medium, the densities of attenuation and backscatter, as well as the color of the medium. Our loss function consists of three terms. Firstly, we employ the reconstruction loss utilizing NeRFs in the dark's loss formulation. Secondly, we incorporate the proposal loss, an integral component of our MIP-NeRF 360-based architecture. Lastly, we introduce the accuracy loss, inspired by Riven et al. LOL, which enforces the transmission of the object to be either 0 or 1, rather than allowing values between 0 and 1. We have observed that this particular loss significantly enhances the network's capacity to accurately learn the scene's geometry and separate between the object and the backscatter. Here is a result on a different set of images from the Red Sea. The former set was from Curaçao in the Caribbean Sea. This demonstrates that our method also works on different water types. In this result, we can see again the limitation of state-of-the-art NeRFs in handling scattering media. We can also see our ability to restore objects also in the far parts of the scene. This is a good time to thank our PhD candidate and excellent diver, Matan Yuval, for the amazing underwater sets. Thank you, Matan. Here is another example of image restoration by removing the medium, this time from Panama. Thanks for listening.